We are going to solve a problem regarding the discrete time Fourier series. This is the question given. Find the Fourier series representation of x of n is equal to sine 0.2 pi n. Then how can we identify in which type of Fourier series this question belongs? As we all know, this is the given signal is a discrete time signal. So naturally that should be discrete time Fourier series. So the question given is actually find the discrete time Fourier series representation of x of n is equal to sine 0.2 pi n. Okay, let us find the solution. It's given that x of n is equal to sine 0.2 pi n. This given signal is equivalent to x of n is equal to sine omega 0 n. Okay, omega 0 n. This signal is of the form sine omega 0 n. Then if we compare these two equations, we can say that omega 0 is equal to 0.2 pi. Then let us evaluate the fundamental period n0. The equation for finding the fundamental period is 2 pi by omega 0. Okay, and substituting for omega 0, we know that the value of omega 0 is equal to 0.2. So on substituting this, we will get omega 0 is equal to 0.2 pi. This and this will be cancelled each other. This is equal to 10. The fundamental period obtained is equal to 10 now. Okay. Now let us rewrite the given signal, given discrete time signal x of n using Euler's identity as x of n is equal to, this is sine 0.2 pi n. That can be rewritten by using Euler's identity as e raised to j 0.2 pi n minus e raised to minus j 0.2 pi n all divided by 2j. Okay. That is what we obtained is sine 0.2 pi n. That can be written as 1 by 2j times e raised to j 0.2 pi n minus e raised to minus j 0.2 pi n. Okay. Now let us split this time using LCM as e raised to j 0.2 pi n 1 by 2j minus 1 by 2j into e raised to the second time e raised to minus j 0.2 pi n. That is the given signal x of n is equal to sine 0.2. Let us mark it as equation number 1. Okay. Now we are going to write down the equation for the discrete time Fourier series of x of n. X of n is equal to, we know the basic equation, that is equal to k equal to 0 to n 0 minus 1 d suffix k e raised to j k omega 0 n. Now let us compare the basic equation with this one. Actually, sine 0.2 pi n is the given signal x of n itself. This is x of n. Okay. So we can compare these two equations because the LHS of both are same. Therefore, let us compare these equations. If we compare the first time, this time, what we can guess is probably dk will be equal to 2j, and then followed by exponent time in both equations. Then here we have j time, here also we have j time, then followed by 0.2 pi n is here, but here it is k omega 0 n. So if we equate the exponent terms together, we will get the equation for k, because we know omega 0 and k is the unknown here if we compare these two equations. Similarly, we have to compare the second term also with this equation, then we will get another value for k. Okay, let us compare. I'm going to compare these two equations. So naturally there may be chance that dk may be equal to 1 by 2j. Okay, now let us conclude that. Okay, and now we are going to equate the exponent term of this equation with the basic equation, that is uh, here we am getting j 0.2 pi. Okay, 2 pi, that is equal to the jk omega 0 n. Okay, then j time and j time cancelled, n cancelled, and what I have is k omega 0, that is in the RHS side, is equal to 0.2 pi. Okay, but we know that omega 0 is equal to 0.2 pi. Okay, now k, therefore k is equal to 0.2 pi. I'm going to take this omega 0 to the right hand side, then that will be in the denominator by omega 0. Now substituting for omega 0 is 0.2 pi. Okay, divided by 0.2 pi. Okay, then that is equal to 1. Now the value of k obtained for the first term, for this term, is equal to k. So naturally this will be dk, as both these equations are equivalent to each other. So this if we substitute for k here, actually we obtained the value of k equal to 1. So everything is comparable here. So naturally this will be dk term and this will be dk. Therefore we can conclude that dk, actually we obtained this dk is equal to 1 by 2j, but the value of k here is obtained as 1, therefore this is equal to d1. Okay, let us mark it as equation number 2. Similarly, on comparing the second term with the basic equation, we can again conclude that minus j. Okay, here we have 1 by 2 pi. One thing to be noted is here it is sigma term, then first term plus second term, so and so. So this will be plus into minus, plus into minus becomes minus itself. So now I take a look between this equation and the basic equation. Then of course dk will be equal to minus 1 by 2j, and exponent time is here and here also. And now let us equate the power of exponent terms together, as we have done in the previous case here. Okay, now equating the exponent terms of this equation with the basic equation. Here it is minus j 0.2 pi n, 0.2 pi n, that is equal to the power of secondary terms e raised to j k omega 0 n. Now n and n, j and j cancelled each other, and the remaining thing is implies k is equal k omega is equal to the remaining thing is 1 by 2 pi. Okay, therefore k is equal to minus 0.2 pi n by omega 0. Again we know that omega 0 is equal to 0.2 pi. So substituting, we get this is equal to minus 0.2 pi n divided by 0.2 pi n equal to minus 1. Okay, now what I obtained is k, the value of k is equal to minus 1. So naturally dk, in the second time what I obtained is dk is equal to minus j, no sorry, minus 1 by 2j. Okay, the value of k in this case is minus 1, so implies that d of minus 1 is for substituting for k equal to minus 1 here, I get a d of minus k is equal to minus 1 by 2 pi j. Okay, now we obtained two coefficients, Fourier coefficients. So first one is d1 is equal to 1 by 2 pi j and d of minus 1 is equal to minus 1 by 2j. Okay, let us mark it as equation number 3. Okay, now I am going to rewrite the equation for the discrete Fourier series. X of n is equal to sigma k equal to 0 to n0 minus 1 dk e raised to j k omega 0 n, where we obtained that n0 is equal to 1 and omega 0 is equal to 0.2 pi. Okay, now I'm going to substitute the values of n0 and omega 0 in this basic equation. Okay, then I'm getting x of n is equal to sigma k equal to 0 to n0 minus 1 is equal to 10 minus 1. Okay, then followed by dk e raised to j k, for omega 0 we have 0.2 pi n. Okay, then this is equal to sigma k equal to 0 to 9 d suffix k e raised to j k 0.2 pi. Now one thing to be noted that the number of Fourier coefficients we obtained are 2. We obtained only 2 Fourier coefficients, d1 and d minus 1. Now let us back to our equation. Here we have k varying from 0 to 9 only. So naturally there will be Fourier coefficients as if k equal to 0, this coefficient will be d0, and for k equal to 1 this will be d1, then d2, d3, d4, d5, d6, d7, d8 and d9. Finally the last coefficient will be d9. So the expected Fourier coefficients are from d0, d1 etc to d9 only. Okay, because by this equation we have k equal to the limit varying from 0 to 9. So naturally we are getting the Fourier coefficients from d0 to d9 only, but from the signal given we found that the number of there are 2 Fourier coefficients for the given signal x of n is equal to sine 0.2 pi n. Okay, that they are d1 and d minus 1, but in our equation there will not be any negative time, I mean d minus 1 time will not be here, so we have to apply the periodicity. We found that the fundamental period n0 is equal to, from these equations, n0 is equal to 10. That means the signal itself repeats for every 10 samples. Okay, For every 10 samples, the signal repeats itself. Okay, that's the meaning of fundamental period. And back to the Fourier coefficient. Okay, here we obtained two coefficients only, d1 and d minus 1, but the problem is that we have positive Fourier coefficients only by these equations, so we had to apply for the periodicity. Okay, d minus 1, that will be equal to d minus 1 plus n0. What does it mean? I have already told that the meaning of fundamental period n0 is the signal itself repeats for every n0 samples. Okay, that means the Fourier series is periodic here. So let us apply the periodicity here. So this is equal to d minus 1 plus 10 is equal to d9. So d minus 1 will be equal to d9, that will be equal to minus 2j. Okay, let us mark it as equation number 4 here. Means the value of d minus 1 is equal to d9 is equal to minus 1 by 2 by j. Okay, now let us expand this equation. Okay, this is equal to, for k equal to 0, this will be equal to d0, and if we substitute for k equal to 0 here, that is equal to e raised to 0, then plus, if k equal to 1, we are getting d1 e raised to j, k equal to 1, then we are getting 2 pi n, plus for k equal to 2, we will be getting d2 e raised to j 2 into 0.2 pi n, plus next for k equal to 3 here, we will be getting d3 e raised to j 3 into 0.2 pi n, plus d4 e raised to j 4 into 0.2 pi n, plus d5 e raised to j 5 into 0.2 pi n, plus d6 e raised to j 6 into 0.2 pi n, plus d7 e raised to j 7 into 0.2 pi n, plus d8 e raised to j 8 into 0.2 pi n, and finally for k equal to the upper limit. Now we are reaching the upper limit, k equal to 9, and we have d9 e raised to j into 9 into 0.2 pi n. Okay, but we have only two Fourier series coefficients as per the given signal x of n. That is, we have only d1 and d minus 1 is equal to d9. We have proved that. Okay, so what we are talking about is as per the given signal x of n is equal to sine 0.2 pi n, we have only two Fourier series coefficients, that is they are d1 and d9 here. Okay, so if we substitute, that means all other Fourier coefficients, means d0 value of d1 is here, d0, d2, d3, d4, d5, d6, d7 and d8, that is equal to 0. Okay, right? That means actually we have two Fourier coefficients, d1 and d9. Only d1 and d9 are present in our signal, and then all other coefficients, this one, d2, d3, everything, all other coefficients are 0. Means d0 equal to 0, d1 equal to 0, 1 divided by 2j. Okay, then d2 equal to 0, d3 0, d4 0, d5 0, d6 0, d7 0, d8 0, and d9 is equal to this one 1 by 2 pi k. So the given signal x of n, that is changing to d1 e raised to j 0.2 pi n plus d0 0, d2 0, d3 0, everything is 0. So I'm not going to write 0 plus 0 plus signs. Okay, finally we will be having d9 e raised to j 9 into 0.2 means 1.8. Okay, pi n. And from equations 2 and 4 we have d1 is equal to 1 divided by 2j and d9 is equal to 1 divided by minus 1 divided by 2j. Okay. Now I'm going to substitute the equation 2 and 4 into this equation. Then I'm getting this is equal to 2 pi 1 divided by 2j e raised to j 0.2 pi n, then plus d9. What is the value of d9? We found that the value of d9 is minus 1 by 2j. Okay, then followed by e raised to j 1.8 pi. Okay, that is x of n is equal to this one, 1 divided by 2j e raised to j 0.2 pi n minus 1 divided by 2j e raised to j 1.8 pi n. Okay, this is the Fourier series. Representation of given signal. Sine. What was the given signal? 0.2 pi n is equal to 1 divided by 2j e raised to j 0.2 pi n minus 1 divided by 2j e raised to j 1.8 pi n. Okay, all other coefficients are 0. d0, d1, d0, d2, d3, d4, d5, d6, d7, d8. All these are 0. d1 is equal to 1 by 2j and d9 is equal to minus 1 by 2j. These are the Fourier coefficients.